Hello, today we're going to continue with structure 1.2 on the nuclear atom. Our focus today is going to be looking at different isotopes. Isotopes are atoms with the same element with different numbers of neutrons. So isotopes have the same number of protons, but different numbers of neutrons. So I'm going to look at, let's do fluorine. Fluorine always has 9 protons. That's what makes it fluorine. It always has 9 protons, so its atomic number is 9. But you can have different isotopes of fluorine. So you might have an isotope of fluorine that has 9 neutrons. So the mass number would be 18 because there's 9 protons and 9 neutrons. Okay, so that's for this isotope. This next one might have 9 protons, but maybe it has 10 neutrons. So this mass number would be 19. So when you're looking at isotopes, they have different numbers of neutrons, but the same number of protons, so they will wind up with different mass numbers. Okay, so let me pull up, so let's say hydrogen. Hydrogen has 1 proton, smallest element, 1 proton. And there are some hydrogen atoms that don't have any neutrons. So 1 proton, 0 neutrons. So its mass number is just 1. Some hydrogens have 1 proton and 1 neutron. So it has a mass number of 2. We call that deuterium. And some hydrogens have 1 proton and 2 neutrons. And so its mass number is 3. That would be tritium. So those are the 3 isotopes of hydrogen. Now, chemically, they behave pretty much the same because if they have the same protons and electrons, they're probably going to undergo the same type of chemical reactions. So you should know that isotopes typically behave the same chemically. They might have different physical properties, and so this one's important. You should know that heavier isotopes will tend to be denser because they have, more protons and neutrons and more mass per volume. They tend to have higher melting points, and they tend to have higher boiling points. And that's all because there's more neutrons available in the nucleus. So let's talk about stability. You have some, let's do carbon. Carbon has 6 protons, and some carbons have 6 neutrons, making it have a mass of 12. Some other carbon atoms have 6 protons and 14 neutrons. I'm sorry, mass number is 14, so it has 8 neutrons. So because of that, we have 2 isotopes of carbon there. This isotope of carbon is going to be a little bit more stable than this isotope of carbon. And in fact, the carbon-14 will decay over time, right? So carbon-14 is what we call a radioisotope, because it will emit radiation over time, naturally. Now, carbon-14 has a really long half-life, which means it takes a long time for the carbon to, for half of the carbon sample to decay from carbon-14. But we can use the amount of carbon-14 remaining to date, and that's like to see how old something is. So that's why it's called carbon dating, because you can see how much is left over, how much has not decayed yet. So you have stable isotopes and you have radioisotopes. And really, the larger the atom, the more neutrons it's going to take to keep the nucleus stable. So there's you don't need to know the band of stability all that much, but you should just know past about 20 protons, you're going to need more and more and more neutrons to hold the nucleus together and keep the protons from just repelling each other apart. That's also why you see more radioactive isotopes as you get into the larger atoms, more protons and more neutrons available. So let's quickly connect this to something cool. So nuclear reactors produce energy by essentially making the energy emitted from radioactive decay, turning that into useful electrical energy. So one of the things that they can use is an isotope of uranium, uranium-235. And so this one is a little bit more stable than a little more useful for nuclear reactions compared with uranium-238, which is another common isotope of uranium. So what they can do is enrich the uranium, it's called, by converting some of those 238 isotopes back into 235. And when the uranium is essentially decaying, I say decay, but a lot of times they will bombard it with neutrons, which will begin the reaction, and then it will cause like a cascade of nuclear reactions as the neutrons go on to continue and bombard more atoms and cause more nuclear reactions to happen. But what they can do is put in control rods, and those control rods essentially stop the chain reaction from happening too much. So it blocks the neutrons from going into other atoms. And those control rods are really important because if you have like an uncontrolled chain reaction happening, that's when you have nuclear meltdowns. So essentially all of these nuclear reactions, you're going to be producing a lot of heat energy, and that's going to be used to warm up water, turn into steam, generate into electrical energy. Now this is just a really basic overview of how nuclear reactors work, but I wanted to point out that yes, we use radioisotopes for nuclear energy, and it's going to be the isotope 235 is going to be more useful than 238 for that. Okay, so let's talk about average atomic mass. So on the periodic table, you will typically see two numbers. Let me pick a good example. Let's use aluminum. Aluminum, let's see, it's 13 and then 26.98. So you'll always see the atomic number, which is the number of protons, which is always the same for that element. Then you will see another number, and this is called the average atomic mass, or just atomic mass. And then the average atomic mass is a weighted average mass based on the isotopes of that element that are present in nature. So that's why you don't see a whole number there. It's also why, so there might be two different isotopes of aluminum. Maybe there's an isotope that's 26 and an isotope that's 27. I don't know off the top of my head. It could be different isotopes. But no matter what, you're going to have a weighted average. So if these were the two isotopes of aluminum, notice that it's not 26.5. So we didn't just take a straight average of those two mass numbers. This would be the average mass if you had 50% of your isotopes were aluminum 26 and 50% of your isotopes were aluminum 27. You would get 26.5. But if this is the true average mass of aluminum, so we know that it's not a 50-50 mix. We know actually that there's quite a bit more of the aluminum 27 because this average is much closer to 27. So I don't know what the numbers are off the top of my head, but you're going to see more of one isotope than the other. And there might be 3 isotopes or 4 isotopes, whatever it is. It will be an average based on the percentage abundance of how much of those isotopes are present in nature. Okay, so what is the average atomic mass of a fictional element X, which exists in 3 stable isotopes, 20% X13, 35% X14, and 45% X15? So your strategy when you're solving these type of problems is you want to change those percents to decimals first. So you have 0.2, 0.35, and 0.45. And then you multiply by the mass. Now in this case, we'll just use mass number. But if you have like the mass in atomic mass units, or you're using like the actual mass of protons and neutrons that are present instead of just the relative mass, whatever information you're given, you will then multiply by the percent abundance. And for the first one, you get 2.6 and 4.9 and then 6.75. Once you multiply that, then you're just going to add them together. And when you add them together, you get 14.25 is your weighted average. So that's kind of your overall strategy, and it works no matter how many isotopes you have. If you only have 2, 4, 5, 6, you just add them all up at the end. Okay, our second example, if you have the average atomic mass of chlorine is 35.45, and if we assume that there are only two isotopes, calculate the percent abundance of chlorine 35 and chlorine 37, and it says to just use the mass numbers, so we don't have any other data about the true mass of those, just the relative mass. So the strategy kind of here is, so if I only have two isotopes, I know that, let's call this one X and this one Y. So that the abundance of the chlorine 35 plus the abundance of the chlorine 37 must be 100%, because those are the only two that are present. Another way to think of that, if you put it in decimals instead of percentages, they have to add up to 1. So if X plus Y equals 1. Now, remember that you change the percents to decimals and then you multiply by the mass number. So in this case, if that's my decimal, X times 35, plus for Y, you would do the 37 times Y. Once you multiply those and you add them together, you will get your average atomic mass, which is the 35.45. So now we have a system of equations. X plus Y equals 1 and 35X plus 35Y equals 35.45. Just solve for one of those variables, it doesn't matter. X equals 1 minus Y. And you're going to plug that in. Like this, and then you will solve for Y. And in this case, when you solve, you get 0.225, which if we change that to a percent, so 22.5%, and we said Y was the chlorine 37. And you can just subtract from 100 to get the other one, so 77.5% for the chlorine 35. Which makes sense that you have more of the chlorine 35 because the average is a lot closer to 35 than it is to 37. And so that's kind of your strategy when you are asked to find the percent abundances. Okay, so we have one linking question here if you're going in a different order. So this unit links to reactivity 3.4 and how can isotope tracers provide evidence of for a reaction mechanism. So effectively we're going to use those radioisotopes that we talked about before. Radioisotopes are going to decay over time because they're not 100% stable, and effectively we can track the amount of radiation that's being emitted to track what's going on, whatever is happening. So in a chemical reaction, if we use a radioisotope of that element instead of the stable isotope, we can see the radioactivity being emitted. Maybe not visually, but we can use some kind of detector to see what's going on. So we can actually follow like where it is if you're doing like a biological experiment, like physically where the radioisotope is located, or you can be tracking like the amount and timing of the reaction based on when the radioactivity is being emitted.